Hello and welcome to another video on Building Performance Architecture's YouTube channel. I'm Rob Hoskin and I am the principal of Building Performance Architecture. Today's video is going to be about blower door testing in passive buildings and other building types. I think it's a topic of interest for a lot of people, and so I hope you enjoy the content here. And if you do like it, please hit the like button on the YouTube browser. And also, I would like it if you'd subscribe to our channel. We're going to be having a lot of more videos coming out based on the presentations that we've given over the years. And the general topic that we present on is energy-related building quality assurance and quality control, which is what our firm Building Performance Architecture specializes in. So, this presentation we gave back in September of 2019 to Passive House, Western Pennsylvania. That is a group that is dedicated towards advancing passive house principles. For those of you who aren't that familiar with passive house yet, that is a building standard that is one of the most stringent energy efficiency building standards in the world right now. It typically leads to buildings that are 75% less energy use than the standard new construction at this time. So very energy efficient buildings. And in addition to the energy efficiency, the passive house program requires buildings to have good ventilation, good lighting, and it usually results in buildings that are quiet on the inside. So an overall great indoor environment as well as low energy use. So the quality of passive buildings is usually very high, on the high end of the quality spectrum. So today's presentation is called The Great Motivator, Blower Door Testing in Passive Buildings and Beyond. So since this presentation was for a passive house audience, I'm going to go into describing passive building strategies and how blower door testing fits into those strategies. The first strategy is making sure that the building envelope is a high performance envelope. And what I mean by building envelope is all the surfaces of a building that separate indoors from outdoors. So it would be the roof, the exterior walls, and the bottom of the building, which is often a floor slab. Sometimes if it has a basement, you'll have the basement walls. So all of those surfaces are the building envelope. And if you have a high performance building envelope with continuous insulation, minimizing thermal bridges, which can be spots where more heat is able to go through the envelope than in other places, minimizing air leakage, and also optimizing passive heating, which is sunlight coming in through the windows and converting into heat, and also passive cooling, which is natural ventilation when outdoor conditions are right for that. If you have all of those things in your high-performance building envelope and you deliver fresh air with energy-efficient ventilation systems, and also use high-efficiency lighting and other devices that use energy, all of those things put together enable the building designer to minimize the amount of mechanical heating and cooling that's required in the building. So the term passive building kind of means, by passive, it means the passive systems, the systems that don't use energy. If you focus on those things first, rather than the equipment, you're able to minimize the size of the equipment and the amount of energy that the equipment uses. So that's what passive building is really all about on the energy side. Now, passive buildings have, or the passive building programs have certain requirements that the project has to meet in order to be certified as a passive building. There are 6 main performance criteria, which are annual heating and cooling energy use are the first 2. Hourly peak, which means what is the maximum amount of energy that would have to be used over a 1-hour period for a whole year to heat or cool the building. So on the coldest day of the year, what's the maximum amount of energy needed to heat the building? And on the hottest day of the year, what's the maximum amount of energy needed to cool the building? So there's limitations on those as well. There's also a limitation on overall annual energy use. And finally, there is a limit on the amount of air leakage through the building envelope. There's some other criteria for passive certification having to do with how the building is constructed, delivering adequate ventilation, and just a number of other things that help to guarantee that the building is going to be a high quality building in addition to a very low energy use building. And one of the good things about passive buildings is that these are not only design requirements, but passive programs require the project team to field verify as many of these requirements as possible. So by field verifying, you actually find out and you know that the building is going to perform according to how it was designed. So looking at the main performance criteria again, and talking about field verification, we have sort of an issue here, which is that 5 out of the 6 main performance criteria can't really be tested during the construction phase or right when the building is finished, because they're talking about annual energy use characteristics. But the last main performance criteria, envelope air leakage, can be tested during and after, shortly after construction, and it is tested. So we talked a little bit already about why testing only one. The reason that we do test for envelope air leakage in passive buildings is because it's fast. You don't have to measure the air leakage for a full year like you'd have to measure the energy use. It's basically a short test that takes an hour or two, depending on the size of the building. It can take as short as an hour or two. It could take a full day, depending on how many things you have to look at and close up before you do the test. So it's easy, it's quick, it's easy to quantify and understand the air leakage because you have one target, that you're trying to stay below that level of air leakage, so you can see whether you pass or fail instantaneously. You can see by how much the building passed or by how much it failed, and how much effort you have to spend to make it pass. And also, air leakage is an important thing to test, because air leakage can have a huge impact on how much how much energy the building uses, and also occupant comfort. Nobody likes to be in a drafty building in the winter. Health, to be able to control the air and clean the air that's coming into the building, and durability. If you have air flowing through building envelope assemblies, that carries moisture with it a lot of times, and you don't really want moisture moving through your building construction materials. So those are the reasons that it's good to do envelope air leakage tests. And this slide basically shows the difference between, or the reason really why air leakage carries so much energy with it. It can have a very dramatic impact on energy use. So all these calculations and numbers and equations here are comparing the energy loss in a 1 square foot area of building envelope that has very little insulation versus a 1 square foot area that is basically a hole that air can flow through. So the general principle being that air can carry a lot more heat energy with it than the heat that moves by radiation through an uninsulated surface. So generally, on the left-hand side, we're looking at low insulation. Generally, walls will have an R21 insulation level, somewhere around that, if they're built to code. We're looking here on the left at insulation level of R0.5, which is a lot less insulation. It's basically no insulation. So 1 square foot of that, with a 0 degree temperature outdoors, 70 degrees indoors, that's a 70 degree delta T, you're going to lose 140 BTUs per hour through that 1 square foot. Looking at a 1 square foot hole in the wall, the amount of heat energy that is carried through, assuming a small pressure differential between indoors and outdoors, 11,000 BTUs per hour, which is about 80 times as much heat energy lost through air leakage than through low insulation. So moving to how we do the air leakage tests. We talked about the why it's important, how much energy air leakage impacts. Now, how do we make it happen? In passive projects, the team consists of the top 5 team members on the list here are the typical project team for any kind of building: the owner, the architect, consulting engineers, general contractor, and subcontractors. So that's what it takes to build your typical building. But for passive buildings, there are 2 other team members. There's the certified passive house consultant or certified passive house designer, who's the passive design professional, and they do the the energy modeling that's required to ensure that the design is going to meet the energy requirements. And then there's the passive house rater or verifier. And that is the person who goes to the building and does the testing and inspection that verifies that the actual building that's built is meeting the passive house requirements. So the rater, verifier, or tester conducts the envelope air leakage test, and also a lot of other different kinds of tests and inspections, because it's not just the envelope air leakage. But if you look at the picture here on this page, this is someone who's testing the airflow through a register. We need to test the ventilation, that enough fresh air is being delivered to the parts of the building that it's supposed to go to. So we do balancing of ventilation as just one example of the other types of tests that we do. So it does take a good amount of experience to know what you're doing when you do the testing for a passive building. There may not be as much classroom training required to become a passive house rater or verifier as there is for a passive house design professional. But again, the rater and verifier is a hands-on, boots on the ground, also needing to know what to tell a construction team when you test their building and the building is not passing. So need to be able to see what's going on, what's wrong, and be able to tell the construction team, okay, here's how you fix this. So there's a lot of value added in the passive house rater or verifier's role. All right. Why is blower door testing the great motivator? So going back to this again, blower door testing is something in buildings that, when we're looking at energy efficient buildings, and we say that there's a blower door test, that's basically something that everybody latches onto right away. Everybody can understand air leakage. Air leakage is something that you can feel when the air is flowing past your body. You feel it. And if you have an infrared camera, you can see the air leakage while you're doing a blower door test. This photo here is one of my favorites. It's a blower door test in a historic greenhouse building. And if you look at the horizontal kind of line down the middle of the photo here, you'll see these dark areas that look like they have streaks coming off of them. They're kind of streak-shaped areas. And that is air leakage coming in through the glass walls of the greenhouse. So envelope air leakage, something that you can see, something that you can feel. It's one number that is the target. And so it's just very simple, it's very engaging, it's very visceral, and I like to say sometimes it makes energy efficiency sexy. It's something that you can latch onto. So it's something like solar panels. When you see solar panels on a building, you know that the building is doing something good for energy in the environment. When you see a blower door test happening, when you see infrared images you know that something good is being done here. So, and also, it's a motivator for the construction team because there's the one target number that the building has to hit, and it's pass or fail. So they know that they have to build the building to be able to hit that number. And they know that if they don't hit the number, they're going to have to do more work after the test. All right, and this slide has those words that I just said. It's a focal point for the project team members. In addition to the contractor having to meet the target, the architect needs to design the building to have continuous air barrier around the whole building envelope in order to be able to limit the air leakage that gets through. And last, just because of all these pretty much, I would say, dramatic and visceral aspects of blower door testing, it just gets more attention than all of the other tests that we have to do on passive buildings. So much so that in the past I've tried to do presentations that are on other aspects of passive building verification, just because everybody already gets the blower door part. And there's a lot more to it than that, but blower door tests, it's just fun. And actually, this video came about because of a previous video was about energy-related QA/QC on passive buildings and other buildings, and one of the comments that I got on that video was, "Oh, I thought you were going to talk about blower door testing." And there wasn't much information on blower door testing in that video, but my response to that comment was, well, we have a whole presentation on blower door testing. So that's why we're doing this video directly after that one. All right, so again, there's a large effort required from the whole project team to achieve the air tightness target. Also, the testing affects the construction sequencing. One of the things that we do is we do a preliminary blower door test right when the overall building envelope air barrier is first completed. So if you see the picture on the left there, the black surface of the exterior wall is an air barrier product that has been applied over the sheathing, and you see the windows there are sealed to that air barrier with spray foam, and there are other things that you can also use to seal windows to the air barrier that might be a little bit better than spray foam. But anyway, so our preliminary test enables us to see whether the building's primary air barrier is airtight, and we can also see any places that it's not airtight. And since there's nothing covering that air barrier during the preliminary test, the contractor can go and fix those air leaks in the primary air barrier very easily and at low cost. So they'll be more likely to be able to have a top performing primary air barrier that helps the building meet the test when the building is done. And in order to do that preliminary envelope air leakage test, the sequence of construction has to be that all of the products that form that whole building envelope air barrier are installed. That includes windows, as well as usually roofing and the wall air barrier, the vapor barrier under the slab, things like that. They all need to be done at the same time, and they also all need to be not covered by anything else. So that actually has an impact on the sequencing of construction. It's a little bit, can be a little bit different than the standard sequencing of construction, especially for large buildings. So it does take some effort to achieve or to do that sequencing. Okay, so getting into the numbers of how much air leakage is, well, how it's measured, first of all, and then how much is allowed. So the metrics, and I'm not talking about the metric system, I'm talking about the generic word metric, which means a unit of measurement or the method of measuring, or how you describe a measurement. There's two main ways of describing envelope air leakage in numbers. The first one is air changes per hour, which means how much of the whole building's volume of air moves through the building envelope when you run the blower door. And the other way is the amount of air leakage per unit of the building envelope surface. And the air changes per hour was common up until probably 5 years ago. It was the main way of describing air leakage in all types of buildings. And then probably about that time, and in others, in different systems, the leakage per unit surface area was done earlier, but now it's really becoming the main way of measuring envelope air leakage, and it's actually the leakage per unit of surface area is a better way to do it, because if you think about where the air is leaking, it leaks through the building envelope. And the building envelope is a two-dimensional surface that has an area. And so the leakage per unit of surface area is really more a direct expression of the envelope air leakage than a leakage number that's based on a building volume, because again, it's leaking through the envelope surface. It's not leaking through the whole volume of the building. And also, one of the other aspects of the difference between these two is the ratio between volume and surface area. So the larger a building is, the more volume it will have per unit of surface area. So if you're measuring a much larger building, it will have fewer air changes per hour of air leakage than a much smaller building will, even if they have the same envelope air leakage per square foot of surface area. And these two things at the bottom of the slide are just comparing building a house that's 30 feet by 40 feet by 50 feet, those dimensions, and on the right is a large building where the dimensions are 10 times as big on all of the sides. The small building has 60,000 cubic feet of volume. The larger building has 60 million cubic feet. The surface area is different by a factor of 100. So the volume is different by a factor of 1,000, the surface area is different by a factor of 100. And the air leakage, based on air changes per hour, the volume air leakage differs by a factor of 10, even though both buildings have 0.2 cubic feet per minute per square foot of surface area. The smaller building has 1.88 air changes per hour, and the larger building has 0.188 air changes per hour. So the air leakage per unit of surface area allows an apples to apples measurement of air leakage between buildings of different sizes. All right, so what do different standards and codes require for envelope air leakage, both the metrics and the targets? Looking at the PHI, Passive House Institute International air leakage limits, they have still been on air changes per hour. For new construction buildings, they have a target of 0.6 ACH 50, and that number 50 there represents the pressure difference between indoors and outdoors that the blower door fan makes on the building. For their EnerFit standard, which is a retrofit passive standard, it's 1.0 ACH 50. So now FIAS, the Passive House Institute US, has gone over to the air leakage per unit of surface area metric, which is the better, more modern metric. So for the larger buildings that have non-combustible construction, so these are typically the larger, more institutional buildings, they actually allow a little bit more air leakage per square foot of building envelope. And then the buildings that are not non-combustible and not as large, the target is 0.08 cubic feet per minute per square foot of envelope at a pressure difference of 75 pascals. So moving to ASHRAE, which is American Society of Heating, Refrigeration, and Air Conditioning Engineers, they actually have a very large influence on energy use standards for buildings throughout the whole world. So their Handbook of Fundamentals suggests air leakages for a tight building, an average building, or a leaky building. 0.1 CFM 75 per square foot. Average is 0.3, and they say a leaky building would be 0.6 or higher. And actually, we're going to see probably on the upcoming slide here, right now the 2015 International Energy Conservation Code, which is an energy code that most jurisdictions in the U.S. follow, their target is 0.4 CFM 75 per square foot for commercial buildings. So you see they're on the high side of average there is what the code allows. The Army Corps of Engineers has been pretty stringent. They have, you think of the Army, you think of discipline. So they have a pretty good air leakage target, 0.25. It's on the tight side of average. The city of Seattle, Washington requires 0.3, and the overall state of Washington 0.4. And we'll talk about Seattle in a couple of slides. They're kind of out in front of the envelope air leakage game here. Some more standards. Top here is a study that was done by the National Institute of Standards and Technology. They actually studied a number of buildings in the U.S., and they found that the newer buildings that they tested came in at 0.36 CFM 75 per square foot, which is actually tighter than the code. And in 2005, they studied 228 older buildings, and the average of that set was 0.92. So here we're getting to the building code, PA. We're in Pennsylvania, so looking at the PA Uniform Construction Code, the residential limit is 5 air changes per hour, and the commercial limit is 0.4 CFM 75 per square foot. The problem with that is that based on the 2015 energy code, which the PA code is, for commercial buildings, the actual test is optional. So, when we're talking about the Great Motivator envelope air leakage test, if the motivator is optional, then the motivation kind of goes away a lot of times to create a building that is more airtight. So you'll end up with leakier buildings if you don't test them. So Energy Star requires, this is between apartments. In multifamily buildings, they require 0.3 CFM 50 per square foot, and that limits air leakage between units. It's what they call compartmentalization, and we like to think of it as not having to smell the fish that your neighbor is cooking. And then lastly here on our standards, ways of testing. So there's a testing standard from ASTM, the American Society of Testing and Materials. Their E779 test method is standard in the U.S. for commercial buildings. It allows you to use multiple fans, and you test at multiple different pressures. The next one, the ISO 9972 from 2015, pretty much similar, although that is a standard that's an international standard that's used in Europe and other places, and that is the standard that the Passive House Institute International requires for blower door testing. And finally here, the ASTM E1186 test, rather than producing quantitative results, the test number that you get, the ASTM E1186 is qualitative, so it is a standard that helps you find out where the leaks are happening. There are a number of ways you can do that. You can use smoke. You can use other things that let you detect the air. And one of the ways that we like the best is the infrared camera, because it's something that, again, produces a striking image. You can really see what's going on. It's something that's recorded visually. People can come back to it and see it at any time. So we like that tool for air leakage location. All right, so finally getting over to Seattle, where talking about motivation, when the building code doesn't require air leakage testing, somehow the team's motivation for making the building airtight isn't as isn't as intense. So what Seattle has done is they've required envelope air leakage testing for single-family homes since 2007, which is earlier than a lot of places. And they also require envelope air leakage testing for all commercial buildings, and they've done that since 2011. So the director of the building department there was learning about envelope air leakage testing, and he basically found that more airtight buildings use a lot less energy, and they had just a mentality over there and made the decision that they wanted their buildings to use less energy. Their community was going to be an energy efficient community, and with airtight buildings using less energy, they decided, well, this is what we're going to do. We're going to make this code in our city. So since 2011, the city of Seattle has gathered a lot of information, both about the effects of air leakage and also about how do we do this? How do we test air leakage? If you look at the picture, you see all the skyscrapers in Seattle. How do you test air leakage on a skyscraper? It's a little bit different than doing a blower door test on a house. So they've generated a lot of information and have pushed the building science forward. And again, just the fact that it's official policy, it's the building code, it's enforced. Those are important tools for getting the construction industry in an area to adopt the best practices, and also to make or to reduce the energy use in a municipality or state or whatever jurisdiction it is. All right, so we've done an overview of envelope air leakage testing, kind of got all of the technical ins and outs of it discussed. And so the rest of the presentation is going to be 10 different buildings that we have tested, just to give examples. So, and we're starting with residential buildings, and we're towards the end we'll move to non-residential. So this first one is a single-family house. It's a rather small single-family house, but very interesting design. And this one is Passive House certified from FIAS. So a little bit over 2,000 square feet. The preliminary blower door test was 0.83 ACH50, and at that time the FIAS target was 0.6. So they had some problems at their preliminary test. That's the point of doing the preliminary test, is to be able to find the problems, and they did, and the final test result was 0.59, just below that 0.6 ACH50 level. The HERS index, which is the Home Energy Rating System, and just a quick explanation of that. The HERS index of 100 means that's the energy use level of a typical new residential unit, or a home or an apartment. And for this index, the lower number means lower energy use, and we like that. So the lower the number, the better the HERS index. So this home's HERS index is 35 when you don't include the solar panels. when you do include the solar panels in the energy model that generates that, the Hertz index is 26, which is about 75% less energy use than the typical new home. So a little bit larger residential building, duplex. This one was developed and built by a couple, and they live in the half of the duplex that's on the left-hand side in this photo, and the other side they actually sold, and the money that they got from the sale of that basically helped to finance the overall whole building. So I think that was a pretty interesting way of getting a passive house project done. This is FIAS certified. So the preliminary test that we did, on the left side it was 0.59 air changes per hour at 50 pascals, and on the right side it was 0.82, which is significantly higher than the target. In the end we ended up, so they found a lot of leaks, they sealed a lot of leaks. In the end we actually tested the whole building at one time, and the test result, surprise, target being 0.6, the test result was 0.59 ACH 50. So this building, if you don't count the solar panels, the Hertz indexes were 44 and 45, so a little bit less than half of the energy use of a typical new house. But the owners put solar panels on the south side of the roof. All of the solar goes to their unit, and so with the solar panels they ended up with a Hertz index of -2, which means that their half of the duplex produces more energy than it uses over a year. And with them being very concerned about the environment, they're thrilled to get that Hertz index, and you can also call that a net zero energy use house. So gradually moving up, excuse me, gradually moving up in size, we come to a development that looks like it's one house that kind of repeats forever and ever down to the vanishing point. It's actually 40 units, and there's 2 rows, but the rows are in sequence. There's a little bit of there's a split between the first 20 units and the second 20 units. Actually, no, it looks like there's 4, so there's 3 splits, but it's still all in one long row. They tested 20 units at one time. We're going to talk about the test of the 20 unit row here. 24,000 square feet, and the final test result here was 61 or 0.61 ACH 50, and this was excuse me, this was going for FIAS certification. Slightly over 0.6, but they still got FIAS certification because you are allowed to round down. Anything below 0.649 will count as 0.6, so they passed the test with 0.61. And the interesting thing about how this project was tested is that, you look here, and they're testing a row of 20 dwelling units, and Passive House requires you to test the whole building at one time, but there are solid walls between the dwelling units, So in order to test the whole building at once, you might have to put in 20 blower doors, one on each dwelling unit. And for units that are about 1,000 square feet, you don't need that whole blower door to do each unit. So the way they handled it here was kind of interesting. They actually left a hole in the walls between the dwelling units. So on the photo on the right there, you see this. It's about a 1 foot by 3 foot opening. They closed it up later before the people moved in. But that allowed enough air to move between the units so that the tester, I don't even actually know exactly how many blower doors he used, but it was a lot less than 20. It was probably either 1 or 2 for the whole row of 20 apartments. And because the passive house target is so low, you're able to test that many units at one time. All right, so this is actually the first passive building that our firm, Building Performance Architecture, did. So this is a 24-unit, 3-story apartment building, and 26,000 square feet. The preliminary blower door test was 0.52, and this was going for FIAS certification. So that preliminary test result was better than the target. So the building was on track, and everybody was glad that it was going pretty well. That test was done before any mechanical openings were cut into the building, and it turned out that that preliminary test was the tightest the building ever tested at. The final came in at 0.83 ACH 50, and it would not have met the passive house requirement. So the contractor actually sent a crew through the building, and they spent about 3 weeks basically combing every square inch of the building envelope. I think they even sent people in above the ceilings in some of the spaces to find all the penetrations through the envelope. They sealed all of them up, and they ended up with 0.63 ACH 50, which rounds down to 0.6, and the building passed the blower door test and all the other tests that we did that aren't as exciting, and got FIAS certification. The HERS index here on the worst case, or the apartment that uses the most energy, was 53, which is about half of the energy use of a typical apartment. Okay, so moving into the world of non-residential. This is a branch library building, and we tested this in 2018, I believe. So the preliminary test result was 0.46 ACH 50. The target for PHI, which was what the building was trying to achieve, was 0.6 ACH 50. And again, surprise, the final test result was 0.59. They passed. And so this, I believe, is the first passive house certified library in the U.S. And another library, but this one actually was a church originally. So this is a retrofit project. And it's a little larger, and there was more work that had to be done. So that they were dealing with an existing building envelope had to figure out how to air seal it. The preliminary test came in at 3.57 air changes. The target was 1 ACH 50 1.0, which was allowed because of the retrofit. For new construction it would be 0.6, but for the retrofit it's 1. They did a lot of air sealing between the preliminary test and the final test. But the final test came in at 1.27, and we're not allowed to round down on that. Can't round down to 1. So this one didn't get the passive certification, but still at 1.27 air changes per hour. If you think about what the code requires for homes right now, which is 5 air changes per hour, this is about 75% tighter than what code allows for a home. So it's still a pretty good building. And if we, this is one of our earlier projects, we learned from doing a couple of these that were primarily air sealed with spray foam. If we had to do it over again, based on what we learned, we would use a different product to do that air sealing, which would probably be a fluid applied air barrier. It's basically just spray foam doesn't necessarily stick to everything, and it can leave gaps and openings, whereas the fluid applied stuff basically forms a membrane that is stuck onto the building envelope. It just works a little better. So another larger building that we tested, if you look on the lower left photo, the building we tested is the white one that's in the foreground. It's a university building. It was built in 1957, and it has a tall classroom tower that's actually 13 stories. It also has offices in that tower, and then the lower part of it is a chapel. Testing this building, the reason why we tested it is because the college that it's located at is planning on doing retrofits of the building envelope floor by floor, and what they wanted to do was to get a baseline envelope air leakage so that they would be able to plug that into an energy model, and then when they go and retrofit floor by floor, they'd be able to see what the air leakage reduction is and how much energy would be saved by that envelope remodel that they're doing. I think they actually might be done with that, with all the floors at this point. I have to get an update on it, but they've done a number of them, and it's been a good project for people to learn about at the university. So here the test result was, for the whole building, was 0.79 CFM 75 per square foot. Now, if you remember, we said that the code requirement is 0.4 CFM 75. So this is about twice as leaky as the current building code. But considering the fact that it was built in 1957, that's not too bad. There's plenty of room for improvement, though, and the retrofits will help a lot. So, going to probably one of the most interesting tests we've ever done was East Liberty Presbyterian Church in Pittsburgh. And if you look at the aerial photo of it on the right, you see it basically takes up a whole city block. It's basically a cathedral. So it's a gigantic sanctuary with a gigantic tower, and then it has the classroom buildings and the administrative wings that are built off to the side of the cathedral-like church structure. So, and this was also one of the largest envelope air leakage tests that had ever been done in the city of Pittsburgh at that time. And if you look at the test result, 0.5 CFM75 per square foot of surface area, it's actually tested out tighter than the university building. This building was built in 1935, so it was 22 years before the university building was built. The conclusion that we came to after seeing how airtight this historic stone building is basically the funder for the project, the Mellon family, basically bought the best construction that money could buy for this building. I mean, to have a stone masonry building test out, that's 86 years old, test out, almost meeting the current energy code standard for air leakage is just super impressive. Although again, the reason for doing the test here in this building was that they're going to do a retrofit, and they did a retrofit project. And so being able to know how much air leakage is reduced during the retrofit can enable the owner to find out how much energy is saved, and also be able to predict the performance of the building over time. And there's a lot more we could say about that. We're going to save that for another video. A new school building. We actually had to test just a section of this building because this project, they didn't incorporate the required sequencing into construction because we kind of came into the project after the construction contract was already signed. They already had planned out exactly how they were going to kind of move through the building as they install different things. So this one, in some parts of the building, the walls were already drywalled, while in other parts at the same time they were still putting up the structural columns, and there was no enclosure at all. So we tested part of the building at one time, and the test result came in not that bad, actually. 0.44 CFM75. And this is our last one here, a living building certified project. So living building, I guess I would say living building is to green building programs what passive house is to energy efficiency building programs. The requirement that kind of drives the need for envelope air leakage testing on this one is that living buildings are required to produce all of the energy that they use on site with renewable energy generation. So if they had a leaky building envelope, the amount of solar panels that they would have to put here gets larger and larger, and at some point you run out of room. If you run out of room on the roof, then you're going to go to the site. You run out of room on the site, well, I guess there's no more you can do to produce all your energy on site. So the goal of having a tight building envelope that doesn't waste a lot of energy becomes important here. This building actually, this is a retrofit project. It actually used to be a municipal garage, and they turned it into something that is a lot nicer than the original. So we did a preliminary test, got 4.4 air changes per hour, and our target was actually, we didn't even end up hitting our target. We wanted to hit 1 ACH 50 in the end. So given how leaky the existing garage was, starting out with our preliminary of 4.4, the contractor did a lot of air sealing and ended up at 2.45 ACH 50. So even though it didn't hit the target that we wanted, again, if you compare it to what the building code now requires for a house, which is 5 ACH 50, so this basically comes in at 50% less air changes per hour than the code requires for a house, which was pretty good. So that was a successful project, and so that's basically an overview of a bunch of case studies that we did. So giving this presentation in 2019, that was a couple of years ago. Since then, we've done a lot of other air leakage tests. We've actually conducted some tests that have come in quite a bit lower, quite a bit more airtight than Passive House requires. And we actually did a house just this past month that ended up with a HERS index of not only 0 or not only -2, but actually -18. So that home is, say, a net energy positive house. So again, I think you can hear the excitement and get a sense for the just the level of interest that blower door testing generates in projects, and it is the great motivator for energy efficient buildings. So with that, wrapping up the presentation here, if you liked it, I would say make sure you press the like button and subscribe to our channel. We're going to be doing a lot more videos on different topics of energy efficient building QA QC. There's a lot to learn, and we hope that you come back and watch our other videos that we're going to put up. Thanks again. This is Rob Hoskin, and enjoy the rest of your day.